In this video, we're going to look at lines. And yes, these are the same lines that you've studied before, where you have equations like y equals mx plus b and so forth. Well, what we're going to do is take a look and see how vectors can be used to express lines in a different way. So essentially, we want to use vectors as opposed to slopes to define a line. Right, so let's start with R2. The reason why I'm starting with R2, it's a little bit easier to visualize as we've seen. And then once you have an idea of how to solve a problem in 2 dimensions, you pretty much have, especially if it's a geometric problem, you have a pretty set way of solving it in 3 dimensions as well. So let's say this is my line, right? Well, what defines a line? Well, it certainly, there is a direction to it, right? It's not quite a vector because a line does not have an initial point and a terminal point. Again, remember, it extends indefinitely in either direction, right? But what is true, for instance, is if I pick any point on the line, let's say I pick that point, I could find a vector that lies on the line, right? So I could call this, let's say, vector v, and then we know this vector, it will have, some magnitude, some direction, and I'll have a component form. So let's say that's my vector AB, right? But that alone doesn't define this line, right? I can't use this vector and just say, okay, well, let's take any scalar multiple of that vector. And the reason why we can't just use the vector and just extend it indefinitely is this. Suppose I had another line that was, let's say, parallel to this one. I could find this vector also. I could find the equivalent vector to v right there. That is still v. Same length, same magnitude. This is still my v. But these are 2 different lines, right? So I can have the same vector. I can have the same direction vector, if you will. But it could be used to define different lines. So the question is, what distinguishes this line from this line? If they have the same direction, well, what they don't have in common is the set of points that they pass through, right? So in other words, this vector here, again, or I should say, this vector, and then in general, this line, they both pass through a different set of points as compared to this line. So the vector is important, the direction certainly is important, but also what we can do is use a point to describe this line. Now, before I add the discussion of the point in, I want to say a little bit more, and I'll focus on this one. So here's my vector v. If I extend it, so v is the vector that starts at this point and ends at this point. But if I extend v indefinitely, so if I were to take a scalar multiple of v, so this portion now of the line would be equivalent to be something like t times ab, and because I am lengthening it, right, then this portion would require that t be greater than 1, right? That portion right there. If I wanted to shorten it, so I'm not going to draw it, but essentially let's say that there's now a dotted portion here. So let's say I wanted to generate the points that are in this portion of the line. Well, I would use the same expression, right? And what I would do is I would have to use a value of t that's between 0 and 1, right? And in fact, let's say I include 0 and 1 there, right? That way I could get back the original vector v, or I could make it shorter, or I could essentially turn it into the 0 vector if I multiplied this vector by 0, right? So if I wanted the portion of the line that essentially starts at this point and then goes indefinitely in that direction, I would have to take all possible values of t greater than or equal to 0, and I would generate that portion, right? But then also, if I wanted to generate this portion of the line, all I would have to do is take my same vector v and now multiply it by any negative scalar. So I'm just going to just use this entire portion of the line, which in fact is called a ray. A ray is an object that has an initial point but has no terminal point. So it's a linear object, right? But it has an initial point, no terminal point. So the ray that goes from this point and then goes in the same direction as my vector will be defined by taking my vector AB and multiplying it by any constant that's greater than or equal to 0. If I wanted the ray that goes in the opposite direction, which would again give me the remaining portion of the line, then t would have to be less than 0, right? Right, so that's the idea. So, but that's assuming that my vector starts here, right? So in order to guarantee that my vector will pass through this specific point, so now let me label this point. I'm going to call it point, so let me highlight it here. This is the point, and I'm just going to call it x0, y0. It's some point in space, right? So if I wanted to describe all the points on my line now, what I could do using vectors, this is what I could use. Since I know this point, I could define a vector that goes from the origin and goes to this point. So I'm going to define that vector, right? And then once I go from the origin to this point, if I then add any scalar multiple of my vector v, then I will generate all the points on the line. And this is how I can distinguish between this line and some other line, even though it might be parallel to my first line. The reason why is this line now, it would have a different point. It would have a point x1, y1, for instance. And then in that case, I don't really want to go through. I'll just kind of do this and go through here. The vector now from the origin to the second point, to the second line, it would have a different set of components. So that's how I can distinguish between two lines that might have the same direction, right? But pass through different points. In other words, this is how I can distinguish between parallel lines, right? So let's see if we can write this down, right? So with a single vector, I am going to come up with basically a vector that will generate all the points here. So first, let's go from our origin to P0. So yeah, let me call this one P0 since I have 2 points there. So the vector that goes from the origin to P0, well, we know how to find that. That's our head minus tail. If I know the coordinates of this point, then it's going to be x0 minus 0, and then y0 minus 0. So I have this vector, right? And this is often called like a position vector, right? Starting at the origin and going to some other point, we usually call that the position vector. So I'm going to call this the position vector, right, of the line. Really, it is a position vector because I can have many of them. I could go to any point I would like, right? So this is our position vector. Next, V, and I'll write it down as I have there, the vector AB. This is called the direction vector for obvious reasons, right? Because this is the vector that defines the direction of the line. Changing A and B will change where this arrow is pointed. I could have it pointed up there or down there, but it could still pass through this point, right? So all points, so basically using our vector algebra, all points on the line may be generated or determined by the following vector, right? And what do? So to get to any point on this line relative to my origin, and we always like things relative to the origin, it makes things a lot easier. I would have to move in the direction of this vector. So I would have to go from the origin to this point, and then I would move in a direction that's parallel to the vector AB. And it has to be every possible direction that is parallel to AB that will generate all the points in this direction and then all the points in this direction. So using our vector algebra, this is what we have. So again, this is the vector that takes me from the origin to the point that the line passes through, or a point that the line passes through, and then I have to add to that, right? And this is my vector algebra. I'm here, and if I want to get specifically to this point, I would have to add AB. If I wanted to get to a point that's further away, I'd have to add some constant multiple of AB, where that constant multiple is greater than 1. If I wanted to get to a point that's closer to x0, y0, but still headed in this direction, I would have to have a scalar multiple of AB, where that scalar multiple is, again, somewhere between 0 and 1. And similarly with the argument that I gave earlier. So what we add to this position vector is any scalar multiple of our direction vector, right? And then we can use our vector algebra and write this sum as a single vector. So first distribute the t. So I'll write it like this, AT, BT, right? And then add the corresponding components, because again, these are two vectors in in R2, sorry. So then we end up with this x0 plus AT, comma, y0 plus bt. And this is the famous vector form for the equation of a line that passes through point x0, y0 with a direction parallel to the vector AB. So let's write that down. So this is the vector form of the line, and this is the line in R2. It's 2 dimensions. Yep, we can see that. So a line in R2 passing through the point x0, y0 with direction vector AB. Right? So what I would say is the direction vector is like it's similar. It plays the same role as the slope, right? Let me just kind of do just a little, because you've used this form of the equations of the line so many times, but this is a very similar form. If you look at it, this is the fixed point that the line passes through, which we describe as being the y-intercept. So here we're using not any point that it passes through, but a fixed point. And then when you multiply your x, let's say it this way, when you multiply your slope by the number x, what you're doing is you're essentially taking any multiple of your slope, which is your rise over run, and then you're multiplying it by your x value, which essentially gives you, and when you add it to your y-intercept, essentially gives you the new y value that the line passes through, right? And you do that, and because the slope is constant, then you have that nice constant change, and you generate all these points in a linear fashion, right? So there is a lot of similarity. Well, there should be, given the fact that we're saying that this form is just an alternative form of this equation, right? Now, over here we have a vector. Over here we have an equation. So we would like this to be an equation as well. And what we're going to do is we are going to give this vector a name, right? So that we so that we can say, okay, here is the name of this vector, and this vector represents a line. So we usually use the letter R, right, as the name for this vector, right? So we use the following to represent the vector equation, right, of the line, right? I can't call this an equation because there's no equal sign, right? I'm not equating anything, right? So the vector equation of the line is, so we use the letter R. So this is a vector. We put a R on top there, and then what we have is, let me write the vector form. Right. And then, as we said, to generate all points on the line, we have to take all possible values of t. So in order to generate all the points on the line, not just the ray, not just the line segment, but the entire line, this is the assumed set of possibilities for t. So t goes from negative infinity to positive infinity. All right, so let me go ahead and box this one off as well. All right, so there we go, the vector equation of the line, and it requires two things. It requires any point that the line passes through, and then a direction vector for the line. So we need to know what direction is the line going in, and then we have this value t. This t, this scalar that we're using to scale the direction vector, is often referred to as a parameter, right? So we refer to t as a parameter, right? And what else can we say with this? Well, now that we have the actual vector, right? Now remember, a vector in 2 dimensions, it has an x component and it has a y component. So what this vector is telling me is all the points on the line, on this particular line, the x values can be determined by that formula, that expression x0 plus at, and then all the y values on the line can be determined by the expression y0 plus bt. So what this implies is that the x values on the line, my variable x, they're all equal to x0 plus at, and then all the y values can be determined by that equation, again with the understanding that t can be any real number. If you wanted to write it like this, you could do this, right? So here we can actually get 2 separate equations. It's almost like we're saying, okay, tell me what how can I find the x values on my line? How can I find the y values on my line? Well, I can use this pair of equations to do it. And these two equations are referred to as the parametric form of the equation of the line, right? So going back to algebra and pre-calc, you may recall studying parametric equations, right? And that's what we've defined right here. So these two equations, one for x, one for y, are called the parametric equations. So the parametric equations of the line. Right? So what we have is there's a vector equation or a vector form, and then we have parametric equations or a parametric form. And again, they're telling us the same thing. And it's kind of interesting. If you notice this is a linear function because we have a number plus a number times this letter x, or sorry, t. And then similarly over here, you have a number plus a number times t. So it almost looks like these are linear functions of t. The x0 plus at and the y0 plus bt. And in fact, they are, right? Now, there's one other form that we can get out of this. Now, each equation here so far, they have a letter. The only thing that they have in common, right, these two equations, is the letter t, is the parameter, right? Now, if a and b are not both equal to 0, this is what we can do. So if a is not equal to 0 and b is not equal to 0, we can solve the parametric both equations for t. So we may solve both equations for t, and this is what we would get. So if I were to solve the first equation for t, I would subtract x0 from both sides, and then because a is not 0, I can divide both sides by a. So I can have x minus x0 over a, that's equal to t. And then I can do the exact same thing for the second equation. Subtract y0 from both sides, divide both sides by b, because I am assuming that b is not 0, so everything is well defined. And then I'll have this. But then this is kind of interesting. This gives me one expression for t. This gives me another expression for t, but it's the same parameter. So what does this mean? It means that this expression here must be equal to this expression here. So we get this. So we get that x minus x0 over a must be equal to y minus y0 over b. And this is another form of the equation of a line. Let me go ahead and box this off. Did I box the parametric equations? Oh, there they are. Let me box these off as well. Right? So, yeah, so this equation now is still an equation, right? And so this form of the equation of a line, so this is called the symmetric form of our line. The symmetric form of the line. And notice, in all three forms, we can quite easily identify the point, the x0, y0, and the direction vector, the vector, the components, the direction vector with components a, b respectively, right? So if it's in the symmetric form, this kind of standard way of writing the symmetric form, we can identify the point that the line passes through. It's this number, and the direction vector is the vector AB. Similarly, it's even easier when you look at the parametric form and the vector form. I mean, they're pretty much identical. The vector form is just writing everything in a single vector. The parametric form is writing two separate equations, one for my x variable, one for my y variable. But again, we can easily look at both of these and say, yep, my line passes through the point x0, y0, and it with direction vector AB. So in both of these forms, the coefficient of t, they form the components of the direction vector, and the constant terms, those are the coordinates of the point that the line passes through. All right, so we got three. It's almost like 3 for 1, right? 3 different forms of the line, in addition to our good old, reliable y equals mx plus b. But let's look at a couple examples here, right? In fact, I think what I'll do with this example is essentially just write down all 3 forms. So let P0 be 1, 2, and P2, let's say negative 3, 4, be points in R2, right? So we have our 2 points. So let's first find the vector equation, right, of the line that passes through these 2 points. So I'm just gonna let me write this as P1 instead of P2. So let me just put the 2 points here, right? So let's say that actually, let me sketch it accurately. All right, so let's say, since this is our plane, all right, we can find the points quite easily. Okay, so P1 is a point 1, 2, so that's right here. So this is P1. And then P2 is negative 3, 4, so kind of up here, roughly. So that's P2. So what we're going to find is the vector. We're going to find the vector, the parametric, and the symmetric form of this line. So let's go through. There we go, right? Now, the first thing we want to do is to define our vector that goes from the point 0, 0 to any point on the line. Which one do we use? It doesn't matter. Let's say we define the vector that goes here, right? So that's going to be my position vector. And then from this, I'm going to add all the possible scalar multiples of the vector that goes from P1 to P2. So I'm going to use this vector now. So this is going to be my vector V that I defined earlier, and this is going to be my vector OP, right? So the vector that goes from the origin to P1, so here's let me write down OP. So this is OP1. This is the vector 1, 2, right? And then let's now write down the direction vector of the line V. And that will be the vector that goes from P1 to P2. So that vector, do the change in X, that's negative 3 minus 1, comma, 4 minus 2. So here is the direction vector of my line. There's a change of -4 in my x, and then +2 in my y, right? So as far as the formula that we wrote down earlier, this is x0, y0, and then this is the a and the b. So now let's write down the vector equation. So let's do r is equal to, oh, come on. Come on, let's get my eraser to work. There we go. Right, so it's the vector 1, 2, plus, and then any scalar multiple of the vector -4, 2. So adding these together, maybe we can go across just a little bit. So what do we have? 1, 2, and then plus -4t, comma 2t. So here is the vector equation of the line, 1 minus 4t, comma 2 plus 2t, right? So here is the vector form. So I'll write this here, maybe do it in a different color. So this is my vector form of the line. Then the parametric form, pretty easy. So just simply state what the x component is. So the x component is 1 minus 4t. The y component is 2 plus 2t. And again, this is now the parametric form. Right? And then if I solve, as long as each of these coefficients of t is non-zero, I can solve for t, and then I can get the symmetric form of the line. So let's do that. So solving my x equation for t gives me x minus 1 over -4 equals t. Solving the y equation for t, y minus 2 all over 2, that's equal to t. Therefore, we have this symmetric form. So again, since both expressions are equal to the same parameter t, then they must be equal. So x minus 1 over -4 is equal to y minus 2 over 2. Now, what's interesting about this is, if I were to take this symmetric form, and let me write down the symmetric form here. If I were to take the symmetric form of a line in R2 and isolate the y, I would get my y equals mx plus b. So I think we should do that. That would be a great way to end this, to really come full circle. So solving for y, so solving this for y, well, what would I do to solve for y? I would multiply both sides by 2. So that will give me 2 times the quantity x minus 1 over -4 equals y minus 2. Then add 2 to both sides. So therefore, y is equal to, let me go ahead and distribute the 2. So 2x minus 2 over -4 plus 2. And then I can simplify this. So y equals, this is -1/2 x plus 1/2 plus 2. And therefore, we have this -1/2 x plus, not 3 halves, 5 halves. So 5 over 2. And this is now our slope-intercept form. So all 4 forms are fairly easily obtained, right? But our focus certainly now and going forward will be on the vector and the parametric forms. And but yeah, having all these forms, it just shows you how versatile the representation of a line can be, right? And the good news is going from R2 to R3 is just as easy. Now, the only thing though in R3 is that there is no concept of a slope-intercept form for a line in R3. So in R3, we're only going to end up getting the vector, parametric, and symmetric forms, right? So R2 is kind of an outlier, it's kind of a special space as far as lines are concerned, where you have this idea of the slope-intercept. But going in R3, you don't really have the notion of a general slope, and that's why vectors really take over. And it's in the higher dimensions that you see the true importance of vectors when you're trying to describe linear equations like this one. So if you want to see what R3 looks like, tune into the next video, and I'll see you then.